Hello, everyone, and welcome to today's live broadcast, a comprehensive strategy for residue analysis in cannabis and industrial hemp, presented by Rick Jordan, the Laboratory Manager for Pacific Agricultural Laboratory. I am Judy O'Rourke of LabRoots, and I'll be your moderator for today's event. We are delighted to bring you this educational web seminar presented by LabRoots and sponsored by Agilent. For more information about our sponsor, visit agilent.com/chem/cannabis. Before we begin, I would like to remind everyone this event is interactive. We encourage you to participate by submitting as many questions as you want at any time you want during the presentation. Just click on the Ask a Question box located on the far left of your screen and type your questions into the drop-down box that appears on the screen. We'll answer as many questions as we have time for at the end of the presentation. If you have trouble seeing or hearing the presentation, please click on the Help Desk button located in the promotional board at the bottom center of your screen. Or use the Ask a Question box to let us know that you're having a problem. This presentation is educational and thus offers continuing education credits. Please click on the Continuing Education Credits tab located in the top right corner of the presentation window and follow the process to obtain your credits. Please join me in welcoming Rick Jordan. I will now turn the presentation over to him.
All right, thank you very much for the intro. Good morning or good afternoon, everyone, I guess, depending on where you are. Today we're going to talk about pesticide residue analysis in cannabis and hemp, and we'll be going through it kind of as a comprehensive strategy approach. So a little background about our lab. We were established in 1995, and we are a pesticide residue laboratory. We do pesticide residues only across multiple sample types and matrices. We're located just a little ways outside of Portland, Oregon, and our facility is 16,000 square feet. We've got 10,000 square feet devoted to laboratory space and about 6,000 square feet of office and storage. We've got 14 full-time employees, and we process about 6,800 samples a year with an average of 13,700 analyses on those samples. Okay, so this question comes up is why are we screening cannabis for pesticide residues? Now this example is from Oregon, a letter that was sent to producers, and you're going to have a very similar situation in other states. And so the context of this letter is it's illegal to use any pesticides on cannabis not found, in this case, Oregon's cannabis guide list, and they must be used according to label. And then this is a key point right here. Despite cannabis producers receiving test results below state-generated action levels, that the producer can still be in violation of Pesticide Control Act regulations if illegal pesticides are detected at any level. And this will actually come back to this one more time. Okay, so we've got some additional language here. Because it is a Schedule I narcotic under the Controlled Substances Act, no health hazards have been assessed, and there's no application, there's no product labels. Additionally, until a scientific risk assessment establishes which ones can be applied, you can only use ones from the guide list, and that's typically a lot of the different oils and things like that. So we've taken our approach to cannabis, and we've used the same approach that we use for other commodities here in the lab. So we're using a multi-residue approach, and it's industry-wide in other areas of conventional ag. It allows us to measure the concentration of approved pesticides so that we can compare those to established maximum residue levels, and then we can also identify unapproved pesticides that were used, or if a pesticide was applied and the label instructions were not followed. So a little note here, for the purposes of pesticide regulation, the Oregon Department of Agriculture considers cannabis grown in Oregon to be an agricultural crop. And that's what kind of leads us into this multi-residue approach, as opposed to treating it completely separate. Okay, so individual states have established pre-sale testing requirements that you're supposed to screen for selected residues to some action level. And again, as the case in Oregon, most states have additional language in statutes or administrative rules prohibiting pesticide use beyond the scope of specified pesticides. and then that's where we'll come back to this slide again, is that even if you have your product tested to the action levels and to the list that's set by your individual state, you may still be in violation of your state's pesticide regulations if any residue is found. Okay, so here's kind of how we went about developing the method that we're going to apply to cannabis and hemp. So we want to use a single extraction that maximizes the number of recoverable pesticides. We want to use a dual platform MS/MS system that's going to optimize chromatographic performance for the compounds we're looking for. The instrumentation needs to be rugged and sensitive to allow for large dilution factors, and we'll explain why that's important here shortly. We're going to use cleanup steps, again, to try to get rid of some more of these co-extracted materials, and then we're going to develop a compound list which covers a state regulatory list and then additional prohibited substances. So this slide is an example of what people refer to as the Oregon list, and so these are the pesticides that are regulated in the state of Oregon. Now, our approach is to give us a list that looks like this. And so we're going to be filling in the gaps with other pesticides. They're all prohibited, and it just gives us a better screening tool. So for the actual extraction, there's really two options that are kind of industry-wide. You've got the catcher's extractions, whether you're using the AOAC version or the European version. And then you've got a solvent extraction that uses a solid phase cleanup. And there's an example of this extraction. This is from a brewer's chemist publication that was developed for most of these same residues in dried hops. Okay, the catcher's extraction, it does require a hydration step because you're typically dealing with a dried plant tissue. This can range anywhere from 10 minutes to 2 hours. It's got a higher level of co-extracted materials, and then you may see some losses in the more polar compounds as a result of this hydration step. With the solvent extraction and the solid phase cleanup, we're doing a serial extraction with acetonitrile, and then that extract is passed through an SPE cartridge, and it does not require any vacuum. You're just going to collect that eluent. You see a lower level of co-extracted material using this technique, and then your recovery for the polar compounds, that's actually going to increase as well because you don't have that water addition. So this slide is a comparison of the two extracts at the same concentration. So we've got 40 milligrams of cannabis flower per mil of extract. And so visually you can see there's a color difference with the catcher style extraction definitely being a little darker. This is the method reference for the solvent SPE technique. It was published by Dr. Hengel in the Journal of American Society of Brewers Chemists. And then here is how we've broken it down and adapted it to cannabis. We're going to start with a 1 gram sample and 15 mils of acetonitrile in a 50 mil Falcon tube, polypropylene tube. We add a ceramic homogenizer, and then we shake that for a couple minutes. Then we condition our SPE cartridge, which is a Strata X, with 5 mils of acetonitrile. And then we're going to pour that initial 15 mils of acetonitrile through the SPE, collecting that in a second tube. We're going to rinse the tube with 2 5 mil portions, transferring that solvent and all the solids to the top of the FPE, and then we'll bring that up to a 25 mil final volume. So I got these little red numbers. This is my dilution tracker, so we're going to keep track of these things, and then we'll total them all up at the end. This, on the left side, is the cannabis extract, the 1 mil to the 1 gram to 25 mils is on the left side. The right side, that's the solution that you are collecting after eluting from the SPE. And so you see we've got a big color difference, and we'll take a look at these matrices on the MS here shortly. And then this is what the bed of the Strata X looks like after you've passed that 25 mils through. All right, so we'll move on to the analytical instrumentation. Again, we use a dual platform approach where we're using both GCMS/MS and LCMS/MS. It gives us a lot of flexibility in the compound list we can put together, and it also allows us to optimize the instrument for the specific compounds. So on the GC side, we're using an Agilent 7890 with the 7010 detector. And then we've got it configured with a midpoint pressure system, and this allows us to do some back flushing, which is really great for this matrix because it's going to help you keep your inlet in much better shape for those longer overnight runs. So we're running a multi-mode inlet, and we do a pulsed injection, splitless at 35 psi, and then we call it a cool inlet injection. So we're dropping the inlet down to 180, and then after injection, we'll ramp it up to 280 pretty fast. And we're using a single 4mm gooseneck liner with a little bit of fused silica wool inside. The column back flush is set up at mid-run, so when the last compound passes that ultimate union, then we'll start flushing the other direction back towards the inlet. We also use 2 different column phases in our GCs, and so we're using an HP35 and an HP5, and we found that this kind of helps us average the chromatography because you've got different polarities of compounds you're looking at. So this gives us the best mix of 2 different phases. Okay, our calibration technique, we're using matrix max calibrations. If we go linear, we've got at least 5 points. Quadratic, we're going 6 points. The calibration range, and this is also very important, is 0.2 nanograms per mil is the low point, and we run that up to 20 nanograms per mil for the GC. We use a 1/X weighting factor. We don't include the origin, and the correlation coefficient criteria is 0.990 or greater. And then the other thing I want to mention is all of our calibrations are done using the external calibration technique, and so there's no internal standard corrections happening at all. These are some examples of calibration curves, again, coming off the GC. You can see we've got great linearity. So here's kind of the rundown of the extraction. And again, at this point here, we're starting post SPE. So we'll take 100 microliters of our extract, we'll dilute that with 900 microliters of hexane acetone into the 2 mil DSPE cleanup tube, and that is listed below. It's a mix of PSA, NCAP C18, graphitized carbon, and some magnesium sulfate. We'll vortex that for 30 seconds, and we'll centrifuge that for 2 minutes. Then coming out of that cleanup tube, we're going to do an additional 2x dilution to where we'll use 300 microliters of the cleaned extract, 300 microliters of hexane acetone, and that gives us a 20x dilution of the extract ready to hit the instrument. So we'll do the dilution tracker again. So we've got a 10x pre-cleanup, and then we've got a 2x post-cleanup, again, the DSPE. So now we'll see where we ended up. We have a factor of 25x just from the extraction and the solid phase cleanup portion. There's an additional 10x dilution from the SPE step, or the DSPE step, and 2 more for the post-cleanup dilution. And so this has given us a 500x dilution from the sample to the instrument. And again, that's going to be a big deal when you start talking about matrix. This picture probably doesn't look all that impressive, and I agree, but it's illustrating what we're talking about. So the first vial on the left, that is the extract coming from the SPE cleanup, the extraction. So the second tube from the left, that's our initial 1 to 10 dilution, and then the next tube is how it looks coming out of the DSPE, and then the final tube on the right is that additional 2x. And so you can see that just visually, we're dealing with a lot of matrix reduction through these steps, which is all nice, but now what does it really look like? So what we've got here is when we're doing these extractions and method development, we like to take a look at everything in full scan so we can see the matrix, not just the pesticides we're looking for. So this particular chromatogram, this is post-SPE. There's no dilution and no cleanup. And so you're looking at the background matrix. And I believe the masses on this were 50 to 500. If you do a 20x dilution, which is the green chromatogram, you can already see how much matrix you've lost. This is no cleanup step. This is no DSPE. This is just a 20x dilution. Now, if you combine the 20x dilution with the cleanup, that's kind of what that brownish trace is. Now look at your background matrix levels. And of the stuff that's all on the right side of the chromatogram, this is where a lot of your compounds are eluting. And so you've gotten them away from the cannabis matrix, and it's going to improve mostly your matrix suppression throughout that region. Now, some method development results. These are the recovery for the GCMS amenable compounds. And so we've got the black line in the center at 100%, and then 70 to 120 marked in red. And again, these concentrations were 0.2 milligrams per kilogram in flower. And we've got two compounds that are outside 120. We're also taking a look at the percent RSDs. Now, in this case, we've got the black line drawn at 10. And so for these compounds, everything is less than 10% RSD, except for these three compounds. And again, this is at 0.2 milligrams per kilogram. Here's kind of a summary table. We'll jump back to the Oregon regulated compounds. And so you can see here's the table displayed. This shows of the Oregon compounds, we got one recovery outside of 120, and then we've got 3 RSDs over 10. This particular reference matrix we used had a chlorpyrifos drift in it, and so that kind of affects that recovery. The drift was about 2 to 3 times our spike level. Now we'll show you what some of the transitions look like coming off of the GC, and we've just selected some here. And again, the concentration that we're looking at is listed at the top of the chromatogram, and that is the in-vial concentration, which would be equivalent to our low point. For dichlorvos, ethoxyquin, it's another common one that we're seeing lately, and miclobutanil, of course, another important one. So summarizing the GC results, the method validation shows that we've got acceptable precision and accuracy for the compounds we're looking for, and the limit of quantitation is 0.1 milligrams per kilogram for 94% of the comprehensive list that we're doing on the GC. Okay, so we'll kind of run through the same scenario here, looking at the LC. So we're using a Agilent 1260 Infinity 2 multi-sampler, and then the MS we've chosen is the 6470. Some of the more other details here, we're using a porous shell phenylhexyl column, and we're using formate mobile phases. And then this multi-sampler pre-treatment, this is, what we're doing here is we're doing the same injection volume, but we're mixing it with the mobile phase A. And so what that does is that helps focus the polar compounds so that we get much better chromatography, which is going to lead to better response. This calibration technique is just about the same as the GC. It's matrix matched. We're going to go 5 points minimum on a linear, 6 on a quadratic. Concentration range, in this case, again, that 0.2 nanogram per mil low point, and we're going to run that up to 10. 1 over X weighting, exclude the origin, correlation coefficient criteria is the same. And again, this is all done with external standards. There's no internal standard corrections made. Same examples here. We've got some of the LC calibration curves. And so we've got 2 of the difficult ones on here. And so you can see how they perform, the acid-quinosyl hydroxy and the diminazide. And then here's, it looks like another group of 3 troublemakers as well. Okay, this one's a little bit less impressive than the GC one. And so we're basically doing 50 microliters of our extract into 950 microliters of acetonitrile, gives us 20x dilution. We'll turn the tracker on again, and we got 20x coming from here. And this goes pretty quick. We've got 25x coming from our initial extraction, same as before, with a 20x dilution factor prior to analysis. So we're back at that 500x dilution from the sample to the instrument. This is what allows us to deal with the co-extracted materials, the matrix suppression. And we've got another vial picture. On the left, you've got the initial extract, and on the right, you've got the 20x dilution. LCMS recoveries, you can see that and this is 144 compounds, I believe. And so everything is 70 to 120. And again, these were done at the 0.2 milligrams per kilogram. And then we've got our RSD plot. There are a few of these that don't behave as well as the others, but we've got the vast majority of them at less than 10%. Again, we'll jump back over to the Oregon-regulated compounds for a summary. And so in this case, we've got 2 RSDs of these Oregon compounds that are above 10. Oh, that's 3. All the recoveries inside, 3 RSDs that are out. And some example chromatography as well. And then the concentration is listed on the slide. They do vary a little bit more on the LC. Let's see, acequinacil, the diminizide, and then the spinosyn spirotetramat. And again, these are some of the more difficult compounds. So the summary again, basically it's the same. The validation shows we've got acceptable precision and accuracy, and then the LOQ is 0.1 for 89% of the compounds that we're doing on the GC. Okay, so this is, I'm jumping around here. Yeah, here we go. So one of the other techniques that you can use is you can use a dispersive cleanup on the LC. And so you've got a number of options here, so we'll just kind of run through these. The first one is the universal cleanup. Now that's the one that we applied to our GC extracts. And it's got great matrix removal. Primarily that's coming from the PSA and the graphitized carbon black. But we've got a lot of compounds that we do not have acceptable recovery. Now, in other sample matrices, you can add toluene, hexane acetone, something to help get those compounds back off those absorbents. But if you're working with the LC, it's going to require a solvent exchange, which is going to add additional preparation steps. The C18 mag sulfate combination gives you a pretty good matrix removal, and it's got okay compound recovery. And then the C18 PSA magnesium sulfate, this has great matrix removal, mostly because of the PSA, but there's definitely a group of 4 compounds we've identified so far that have very poor recovery, and that's the diminizide, spinosad, spirotetramat, and spiroxamine. This is a plot of the different matrices, full scan background on the LC versus these cleanups, and it's kind of hard to read, but the black one is no cleanup, and then we've used the different cleanups listed in the previous slide. And so you can see that fatty cleanup, the one in green, it gives us adequate matrix removal so that we don't have as much background. So we want to use the cleanup that's got the PSA in it, but we've got some problem. And so the question is, how can we improve these recoveries without sacrifice to the cleanup benefits of the PSA? So what we've come up with here is that you can add methanol at the dilution DSPE cleanup step to improve the recoveries of those compounds. So the question is, how much methanol do you need to add to get those compounds back off the PSA, but not start bringing the matrix along with it? And just a note, and it's a very important note, that it doesn't matter what you do, you're not going to get diminizide back off the PSA. So if that is going to be something that you're required to do, you're going to have to do a pre-cleaned analysis, determine diminizide, and then you can proceed with this if you'd like to. This plot, or these pictures here, these are the 5 different methanol levels. So starting on the left side, we've got 50% methanol addition, and then that's rolling across to the right side where you've got 10. And there's a little bit of color difference, but you're not really seeing a large difference at this step color-wise. So now we'll look at it matrix-wise full scan. So the black trace on the top, that's 50% methanol addition, and then it scales down to 40 in the red, 30, 20, and 10. So you can see at 10% methanol, we don't have a lot of matrix coming back off as compared to the 50%. So what we want to do is determine how much methanol we need to get the compounds we're interested in back off the PSA and then leave the majority of the matrix behind. And so this is the summary of the results that we got from this methanol addition study. And then we kind of settled on 30% looks like it gives us recoveries that we're looking for without getting too much matrix. You could probably dial this into 35 or 40, for example, looking at the saflufenicil recoveries. So this is what we've set up for a 30, and I would suggest that if anybody's going to use this approach, that they go through this whole process themselves. Your equipment might respond differently, and there may be another methanol percentage that gets you where you need to be. So we're going to take 500 mils of the extract. This is, again, post-SPE column. And we'll add 300 microliters of methanol, 200 microliters of acetonitrile into the 2 mil cleanup tube. And we're using the fatty cleanup, which is a combination of the PSA, C18N capped, and the magnesium sulfate. Standard procedure is before, 30-second vortex, 2-minute centrifuge. And then we're going to come out of that tube with an additional 10x dilution factor, 100 microliters of the extract, 900 microliters of acetonitrile. And then we'll look at our tracker again. So we've got 2x at the beginning, a 10x at the middle. It gives us 20 for this step. We'll take another look at it. 25x from the extraction in solid phase, 2 before we do the methanol-assisted cleanup, and then we do another 10x. So we're right back at that 500x dilution from sample to instrument. So to kind of summarize, solvent extraction with a solid phase cleanup, that's going to result in a clean initial sample extract. And the whole thing we're trying to do here is we're trying to deal with matrix so that we can get around suppression issues. Using a 2-platform MS-MS system gives you much more flexibility for optimizing the performance of specific compounds and doing larger compound lists. It gives you the ability to choose which platform is best for a specific compound. And there's compounds that cross over between the two instruments. So if you have a particular sample or a particular strain that's giving you some interference for a compound on one platform, you can set it up and analyze it on the other one, and you can use it as a confirmation tool. And then you need to have rugged and sensitive instrumentation so that you can get these large dilution factors, 500x, from the sample to injection, reducing downtime and maintenance. So one of the comments I get a lot is when we're talking about this method is people say, well, it's not that big a deal, you're just doing a dilution. Well, a dilution is a more effective cleanup technique than doing B.Sc, especially related to cannabis. And if you can combine those two things, then you're just that much better off. Then you can design specific cleanups tailored to the different platforms and, again, to different compounds. The one we use for our GCMS-MS compounds, we're using this universal cleanup, so we're getting the advantage of the PSA and the gravitized carbon black. Then on the LC side, the fatty cleanup, again, it lets us use that PSA, and then we can use that methanol assistance technique to help us get those compounds back off the PSA. So some of the suggestions for future work that we're looking at here is we are looking to scale down the initial solvent DSPE cleanup phase to where we would be, instead of maybe using a 500 milligram bed, we'll drop that down to 100 or lower. We'll look at alternative DSPE cleanup materials in addition to the PSA and some of these, and some other tricks and techniques to kind of get those recoveries back up. And of course, we take the same approach that we do with all of our commodities, is we just continue to pump up that compound list for compounds that we're able to extract and analyze with the others to give us acceptable recoveries. Okay, I'd like to thank Dan Miller and Lily Asamana and the entire staff of Pacific Agricultural Lab for putting up with a lot of the interruptions and hey, try this, can you shoot this for me, and what does that look like as we went through this process. So thank you very much, and I guess we can open it up for questions.
Thank you, Rick, for that informative presentation. We will now start the live Q&A portion of the webinar. If you have a question you'd like to ask, please do so now. Just click on the Ask a Question drop-down box located on the far left of your presentation window. Type your question into the box that appears on your screen and click the Send button. We'll answer as many of your questions as we have time for. Let's get started. Our first question is, Do you see a role for time-of-flight mass spectrometry as a semi-targeted qualitative screening method? In this way, unapproved pesticides may be identified, and samples that are positive for approved pesticides can be sent for quantification. Could this help reduce overall workload?
The time of flight and other accurate mass instruments, they definitely are going to play a role in screening pesticides, both in conventional agriculture and in cannabis and hemp. The FDA has been evaluating this technique for import commodity testing, where they have very large target lists, and there are a number of individual states that use the accurate mass approach for their initial screening technique. I think that for cannabis, some additional sensitivity is going to be needed, and a better understanding of the matrix effects that a time of flight or accurate mass system may give you. But it'll change the way the workflow is done, but it could be a big advantage.
How did you identify the list of pesticides beyond the Oregon list?
The way we did is we started with the target list that we have developed here for our comprehensive screening in both ag commodities, and then again we took a really good look at our hops list. It's the same process we use for all of our matrices. Is we'll prepare a set of full spikes in matrix, and we'll analyze them and we'll see what works. And based on those results, we can work on the trouble compounds, and it also makes it really easy to evaluate and add new compounds as we move forward.
How did you determine which pesticides were better analyzed on GC triple quad versus LC triple quad?
You can usually make an educated guess on which platform to start with. Poor performing compounds can be moved to the other system to see if the performance increases or decreases. A lot of times you'll want to set up a compound on both platforms. Bifenthrin is a great example of that. It works really nice on the GC triple quad system, but some strains have a really strong matrix interference that causes problems with doing bifenthrin on a GC run. And in that case, we can move it over to the LC and we can use that data.
Okay, we have time for one more question. Can you comment on the California list? Do you see potential problems if analyzed completely by LC triple quad?
It looks to me like you should be able to do the California list on the LC only, but it is certainly not going to be optimized. For example, Coumaphos and PCMB, they can be problematic compounds on the LC, but they should perform very, very well on the GC. It also matters if you're just trying to hit state action levels, or if you're really trying to get to a low LOQ, like in our case, 0.1. If you've got two platforms, then you can pick and choose that'll let you optimize the compound response, which then lets you get back to these large dilution factors that I keep talking about. Using an LC alone, the maximum dilution factor, it'll be determined by the poorest performing compound. So if you move those to a GC, you may be able to increase your dilution factor and then take advantage of a lot of the stuff that we discovered during this talk.
I would like to once again thank Rick Jordan for his presentation. I would also like to thank LabRoots for making today's educational webcast possible. Before we go, I want to let everyone know that today's webcast will be available for on-demand viewing through June 29th, 2018. You will receive an email from LabRoots letting you know when this webcast will be available for replay. Please share that announcement with your colleagues who may have missed today's live event. That is all for now. Thank you for joining us. We hope to see you again soon. Goodbye.